Hi friends, welcome back. So last clip we talked about ordinary subset. Now we talk about proper subset. So the textbook definition here looks really simple, but please be warned that lean is about to get 5 times more difficult on this subset compared to the previous one, because we don't have a direct concept of proper subset at all. So let me show you how they actually do it. So it looks like the subset is to start with, but nowhere in the library is proper subset spelled out. So instead, Lean call out to an exotic library called order theory, where the strict subset symbol will be binded there, but not in the set theory folder. So let me pull out the real source code here. So quick recap from last clip. So we implemented the LE instance on set so that we can use a less than or equal to sign on two sets to mean a subset relation. And back then, it would just look like a convention for notation. But that one actually is making subset an order operation on set. So it's making set as an order. And today we're going to tell you the full story about what order is. So keep this in mind. Subset is modeled by less than or equal to sign. And then for the proper subset, just like membership type classes how the in operator for sets, we have two built-in type classes that holds the meaning of ordering. So LT holds the less than symbol, and the has subset holds the strict subset symbol. But look closely, they are just both empty template for notation. We don't have a logical statement about proper subset yet. And the instant here is to model proper subset using only the less than operator. So should we just go ahead and implement LT on set to finish the job? The answer is no, because mathematically set plays many roles, and in Mathlib, those roles form many hierarchies of type classes. So when your role fits in one of this hierarchy, you should only implement the most specific one from that hierarchy, and everything upstream the hierarchy will just automatically be applied to you. So LT is too far upstream to implement directly on set. So in this LT hierarchy, we actually have the most specific type class as the Boolean algebra. So Boolean algebra extends distributive letters, which extend letters, which have same letters, and then partial order, and then finally, and pre-order extend LT. And that is why we implement Boolean algebra instead on set, instead of LT. And less than here just come up from LT from the hierarchy. And this is how Turnley models hierarchy as well, but it's quite a different story, and we'll talk about it in later videos. And if you look at the type class pre-order here, which is the second to last in the middle of the hierarchy, here it defines what less than mean. And remember, to fully implement a type class, we need to actually have actual implementation of every method inside type class. But here, less than have a default definition. So here, this one line is the source statement of proper subset, but it has nothing to do with set yet. So we just need to implement Boolean algebra on set. So notice we just override the LT method. And be careful, we must override with the same shape of function because every method in type classes have a prescribed type. And here we can replace less than or equal to with the subset symbol, and lean just allows it because the former is built using the latter in previous video. But it is not an implication yet, it's a function. So lastly, has this S subset binds the strict subset symbol to less than. But we are not done yet. In order for lean to use the proper subset symbol without calling the .it method from every set, Mathlib have to create 2 other theorems just to make things look prettier. Because only these 2 theorems put the proper subset and the subset in one statement. And notice the second one is the one introduced by the textbook. The second one is what the textbook articulated. And then the first one is the copy from the LT method, and the second one is what textbook articulated. So the RFL as the proof of the first one just means that to prove by reflexivity, which tries to find theorems that matches the goal or the reduced form of the goal. So in this case, the theorem is just LT from Boolean algebra implementation. So this is the full picture of how lean models it. So the strict subset symbol lives in lean's kernel, and the meaning of the strict less than lives in the pre-order in Mathlib's order theory. So for sets, Mathlib does not redefine anything. It inherits the whole Boolean algebra into set, and finally make the proper subset symbol unwrap to the less than operation. So across many theories, proper subset finally emerges. So the question is, why does lean do that, do all of this work? And the surprising answer is that it allows the proper subset to use theorems that are already proven in other theories. So for example, subset has this property of being reflexive, transitive, and it is antisymmetric. And proper subset is a stricter version, which basically turns the reflexive to irreflexive. And all these properties are already proven for all the theory operation, like the less than operations. So this is very time-saving if you want to define a new relation that looks just like something else. So just to show them on the screen, if you were to define them manually for proper subset, and it looks like we don't want to do that. So now let's compare with turn length. So last clip we introduced relations called subset with a default variant for just the ordinary subset. And now the prop modifier lets you put several variants that a single relation names can contain. So for the proper subset here, we just put in a variant called proper, so which reuses the default variant and add a new not set equal statement. The set equal is just a mutual subset relation between A and B, which we will formalize in the next video when we talk about equality systematically. So turn length states this very explicitly, but does it not worry about the same problem that lean has? The answer is yes. We still have the same work to do, but we don't want to do it now. And we don't need to do it now. So as we came across more perspective on what a set is essentially, and we will add all of this perspective using a special block inside the structural block. You will see them when we get there. But for now, we want to keep our mind focused because there is the most helpful way to appreciate the concept itself without worrying about the modeling underneath. And that's what only turn length allows us to do as a proof assistant. The next clip is about set equalities, and please leave a comment if you're stuck on any step. So I hope you enjoyed this video and see you next time.